Hello, I'm Belton-Schure. I'm presenting my design and initial prototype of a thermoset reinforced composite additive manufacturing technique. Why would one even want this? Reinforced composite material has high specific strength, being used in aerospace and high-end automotives. However, it is difficult to manufacture, requiring expensive molds. This means production for small volumes is expensive. Additive manufacturing enables shapes previously not possible and lowers expenses for low production runs. There is only one other competitor in this market. It is a company working out of Oak Ridge National Laboratories in the United States. They serve the United States military and do not focus on consumer or business clients, therefore there is a void in the market. Two designs were put together for this project. The first utilizes a static mixer to combine resin hardener and reinforcement. The fluid is pumped using peristaltic pumps. This allows for proportional metering of the resin and hardener. The static mixer uses a complex series of internal corkscrew shapes offset by 90 degrees from one another. This makes it difficult to manufacture cheaply with a material that can stand up to high temperatures. The resin and hardener have an exothermic reaction that can achieve high temperatures. There is a solenoid valve that controls the pumping of isopropyl alcohol, a solvent that can clean the mixture out of the system so that the mixer can be reused. There is a solenoid at the end which controls when there is extrusion. The second design uses a screw extruder with pin mixers and a metering section. This is fed by two metering valves which control the fluid flow rate. This fluid flow rate is how one controls the mixing ratio. Distributive mixing is when particles are mixed uniformly in space. Dispersive mixing breaks down the size of particles. Distributive mixing is desired to create a uniform mixture. Dispersive mixing is unwanted because it can reduce the aspect ratio of the carbon fiber, weakening the material. Pin extruders are good at distributive mixing. However, they are difficult to manufacture at small sizes due to the shear forces on the pin and the reduced wall thickness. A Saxton mixing design is easier to manufacture. It is cut flight in a traditional lead screw. However, it also dispersively mixes, which is undesirable. A Saxton mixing screw was chosen for ease of manufacturing. Design 2 was also chosen overall because it offered better simplicity and less cost. The expense of the static mixer would be very large relative to the expense of the dynamic mixer. This comes down to the complexity of the geometry. I began by taking a 60mm round stock and taking it to size. An 8mm hole is drilled 57mm deep. A 3mm hole on the other side is drilled to meet the 8mm hole. Two sides 180 degrees apart had 10mm taken off. This allows for a flush surface for the brass nozzle to sit against. Two 4mm holes were drilled 37mm apart, symmetrically around the 8mm hole in the center. These 4mm holes will be tapped to create mounting points for a flange bearing. Two inlet ports were drilled into the 8mm hole. Each hole was 11/32 of an inch. The initial size for a G1/8 female thread. The G1/8 and M5 threads were cut using plenty of lubricant. This allows for brass barb nozzles to be used as inlet ports. A center drill was used to create a tailstock mounting point on an 8mm lead screw with 4 flights. 5mm space cuts were made to create the mixing sections. 6 cuts were made over 30mm. The final length of the screw is used to meter the fluid. A test assembly was performed to make sure all components fit with proper clearance. A motor mount and screw housing mount was 3D printed. A wooden board was used to mount electronics and the solenoid valves. The solenoids are being controlled by an Arduino. They are being tested while mounted to the board. A test of the stepper motor's velocity mode was performed. A few problems were encountered along the build. First, a PSU was destroyed when a mounting screw connected a trace to the casing. Second, an Arduino was destroyed by not correctly isolating its ground from the 24-volt power supply. Finally, when creating my first screw, it broke while in the lathe due to too much stick out. Finally, the assembly was plumbed and tested with water. The pumps and screw work well with isopropyl alcohol. However, when testing with resin and reinforcement, the fluids were too viscous and dense to be pumped. During the build, metering valves were replaced with pumps for improved performance. Changes in design for a second iteration would be having smaller tubing. The large diameter tubing causes large quantities of waste material and an unwieldy extruder due to the large tube bend radius. Better viscous fluid feeding is also required. Pumping from the bottom of the container straight down and using a positive displacement pump with internal gearing rather than a peristaltic pump would be an adequate solution. The pump change allows for a greater pressure difference to be created. Thank you for listening to my report. Have a good day.